Hello, everyone. My name is Jeffrey Smith, and I'm at the University of Nebraska-Lincoln. And today, I'm going to talk about network imputation methods, particularly doing that in R. And I'm going to go ahead and share my screen. So this presentation is based on past collaborative work with John Morgan and James Moody. And I'm going to start by laying out the problem that we're trying to solve. And the basic premise here is that researchers often are faced with network data that is incomplete, or that there's missing information. So, for example, you might have non-respondents, where in a traditional survey, for example, in a school, maybe a student is absent or refuses to fill out the network portion of your survey. In that case, you wouldn't have any information on ties going out from those students, no outgoing information for any of those non-respondents in your survey. More generally, you might have missing edge information. So you might, even if there are actors who are participating in the survey, there might be missing information on whether or not there's an edge between those two actors. For example, imagine you were doing a cell phone Bluetooth study, and two of your participants decided to turn off their phones for a week. So during that week of data collection, you would not be able to determine if there was an edge, a tie, between those two actors. And so that's the general problem we're trying to deal with. And so past work, looking at the effect of these types of missing network data suggests that having missing information does not necessarily or sort of automatically invalidate a study, as the bias is not as sort of large as we might imagine. But it does cause problems with, predictably, as missing data increases, the bias goes up, and this raises sort of hard questions about what a researcher ought to do when you have incomplete information, in order to sort of limit this effect of common source of bias. So visually, it might look something like this if you have missing data. And so what you're looking at is on the left hand is an example true network. And on the right hand side, I have the same network, but the nodes are colored. And in this case, the red nodes are, we imagine these folks are non-respondents, so that a researcher would have no information about all of those red nodes in terms of their outgoing information. We can assume, for example, that they did not fill out the network portion of the survey. And so what you have here is the same basic picture. So the left-hand side is the same picture from the previous picture. The right-hand side here is designed to give us a little sense of why having missing information, in this case in the form of non-respondents, might be a problem. Why is it sort of troublesome to have an incomplete network picture? So the idea on the right-hand side is, imagine we took out or weren't able to consider those folks who were not part of our survey. So basically remove all of those non-respondents from the network, construct the network without them, and then use that to try to do our analysis. What would be missing if we were unable to consider those folks in our analysis? Well, we can see sort of most obviously, if we remove all of those red nodes, our non-respondents, that it looks like one of our actors is an isolate, when in fact, they're really not an isolate. They just happen to be friends of two other people who didn't fill out the survey. Similarly, the network on the right-hand side of those non-respondents removed, the groups in that network look less sort of interconnected, less cohesive, in part because the non-respondents, those folks who didn't fill out our survey, in reality are playing an important part in keeping those groups together. And just more generally, it looks like we sort of underestimate how connected that network truly is. And so, intuitively, the problem is that network measures are based on dependencies, the direct and indirect connections between our actors. And so that's difficult to capture if we have an incomplete picture. And in fact, past work, including some of our own, does show that having missing data of this sort does negatively affect commonly employed network measures like centrality, so indegree, closeness, betweenness, and so on. Centralization on the same kind of measures, typological features such as component size and distance and bicomponent size. And so it's problematic if you're using these measures or these metrics, which are potentially measured with bias, as predictors of other outcomes, health and attitudes and so on, or as the outcome itself. Also problematic if you're going to use networks which are biased in some ways as inputs into simulations, for example, on infection spread. And so if you're going to use networks that are biased in any kind of analysis, you run the risk of your results being potentially biased. So what you see here is results from past work, which shows first what you might expect, that as bias, as missing data goes up, the level of bias increases. So you can see on the x-axis of that first column, the percent missing goes up, the bias increases. It does turn out that the scenario or the case of interest, the features of your analysis really structure how much or how quickly the bias goes up as missing data increases. But yes, in general, the trend is more missing data, more bias, and it's particularly so if the network is small and if you're missing nodes who are in the core of the network. So if you're missing really central actors and you have a small network and you have a fair amount of missing data, then the bias of having missing data is particularly strong. So the basic idea is that we know that missing data is likely to be a problem, or at least it could be a problem, especially in certain scenarios. Okay, and so the question for the rest of this talk is, what should we do? So you're a researcher, you have missing information, you have missing data, you know it could potentially bias your estimates, lead to incorrect conclusions. What should you do? And the basic answer is that you can try to impute, right? If you have missing edges, you can try to impute what that missing information, those missing edges might look like. And so we're going to go over what are your options and how to actually do that in R. Before we do that, I want to be explicit. I want to be clear about what I'm sort of assuming the missing data might look like and what assumptions about what information the researcher is working with. And so the basic assumptions are that you are working with missing data of the following form, where we're assuming that the missing data comes from non-respondents. And so in the figure on the right, I have the true network with what missing data might look like if there were not non-respondents, and they're colored in red. So what does it mean to be a non-respondent? That means that you have no information on sort of outgoing ties from those actors, in this case, E and F. And so in this case, for example, we don't know if E would nominate D or E would nominate C. We're missing those edges. We also miss the edges between the non-respondents, E and NF. And all those missing edges, the edges that we should have, but we don't because we have no information about those outgoing ties from non-respondents. They're colored in red. So that's the first assumption, is that we have people not filling out the survey, telling us who they would have nominated. And so we have missing edges based on people, non-respondents. Okay. Second assumption is that while that's true, we are assuming that respondents, so in this case, person A, B, C, and D, we have full information about those folks who they nominated, for example, as friends in our network survey. And we're assuming that they can nominate non-respondents, E and F. So in this case, we know that actor D nominates E as a friend. So we don't know if E nominates D, would have nominated E, if E would have nominated D back as a friend. We know the D to E edge exists, as well as we know the A to E edge exists as well. Third assumption, less stringent in this case, we're going to assume that we have sort of other kind of information, attribute data on both respondents and non-respondents. So this might be education, age, gender, and so on. And we're assuming that we have that for all actors in the network. And this might not always be possible, but it might be if, for example, you had information on administrative records, or people filled out, or non-respondents filled out some of the survey, but not the network portion, or perhaps they filled out past surveys. You can use that information to sort of fill in the attribute data for those folks who didn't do the network portion of the survey. If you don't have that information, that's okay. It just sort of puts a limit on a little bit on how much information you can use when imputing ties, but the basic strategies will be very similar. And so let me just say one more thing about the second assumption, that respondents can nominate non-respondents. That basically just means that the non-respondents, while they don't fill out the survey, they're basically able to be nominated. So they're effectively on the roster. All right. So what are your options? You have missing data of this form where non-respondents don't fill out the network portion of the survey. There's no information about their outgoing ties. So how can you deal with the fact that you have this incomplete network picture? I'm going to go over three different options, three different sort of strategies for dealing with missing data. Listwise deletions are the easiest, simplest version. Simple imputation approaches, and there's sort of three versions of that, and then a more general approach, model-based imputation. Okay, so first, let me start with the easiest version of listwise deletion. And so on the left-hand side here, you see again the same picture you saw before, with the true network with non-respondents and missing edges highlighted in red. Okay, so you're a researcher, that's the network you're dealing with. You only get the information from A through D. What do you do? Okay, if you choose to do listwise deletion, this basically implies taking all the non-respondents and deleting them and all the incoming and outgoing ties and constructing the network without them. And so you are effectively just analyzing a little piece of the network, just the ties between the observed nodes. You can see there's no node E and node F are not in the network, and there's no ties to and from them, of course. This ends up being, in practice, a pretty poor option. As you can imagine, you're missing a big chunk of the network potentially. Fairly common approach, easy and simple, but it does lead to probably the highest level of bias. Okay, second class of options is simple imputation, and there's really sort of three versions of this. And with simple imputation, the the first thing to note is that here you do begin to put the non-respondents back into the network, in this case, node E. And basically the idea is to start by constructing the network with all the observed ties included. And so we see an edge from D to E and A to E in the true network and the observed network. And so we start there. And then the question becomes, okay, once you have that sort of the raw data and what it looks like, the question becomes, okay, should you impute any other ties? And the idea is that if a respondent like A or D nominated a non-respondent to E, then there's a pretty good chance, or it's a very high likelihood of an edge going from that non-respondent back to the respondent who nominated them. And so the idea here is to begin with putting in the observed network data, starting there, relying very heavily on that, and then doing very sort of light imputation on edges that have a very high likelihood of existing. And there's sort of three options of dealing with this high likelihood ties. Basically, the question becomes, should we impute or add an edge going from non-respondents like E back to the respondents like A or D who nominated them? And those are three options of how to kind of impute those missing edges. So you don't know if a tie exists between E and A and E and D. And then the asymmetric option, you assume it's asymmetric, right? That there are no ties going back or no return ties, okay? In this case, we would get it right with E to A, but get it wrong from E to D. In the symmetric option, we assume it's always reciprocated. In this case, you'd get the E to D right, but the E to A wrong. And the last one is probabilistic. And so you basically flip a coin to determine if you add that edge, in this case, the E to D in the E to A. And you would flip it based on the observed reciprocity rate in the network, based on those observed ties just between the observed nodes. In this case, that would be 0.25. And the last approach is a model-based approach, and this is much more general. This is at the very bottom of the screen here, and it's a much more sort of general approach to imputation, and I'll show you that more clearly on the next slide. So with model-based imputation, the basic idea is that you start with the observed network. You estimate, so you use exponential random graph models, which will assume, I won't go into it too much here. I will sort of assume you are somewhat familiar with these models from other tutorials, where you predict the ties, absence or presence of a tie, between all ij pairs in the network, based on things like edges and mutual reciprocity rate and homophily and these types of things. And this is conditioned on the missing data. And so with the model-based approach, you first estimate an exponential random graph model on the observed network. So you take the observed network, you estimate using a statistical network model, predict the absence, presence of a tie between all ij pairs. Then, let's go down to the next slide. You take this estimated model, which captures the tendencies for ties to form. And then you basically use that to impute where a tie is likely to exist or not, in those cases where you have a missing edge. And so, for example, you take the observed network, you estimate a model using homophily terms. And people who have the same gender are more likely to have a tie. If that's true, then when you go to impute your ties, if there's an edge between, if E and D, for example, are the same gender, it's more likely to impute a tie going from E to D. Or if mutual ties, reciprocated ties, are more likely to exist than asymmetric ones, then we're more likely to impute a tie from E to D than from E to C, for example. And when you do this type of prediction using the estimated model, couple things to note. So first, you're going to hold the observed ties constant. So everything that's observed that isn't missing, you're going to hold constant. So you don't let that to change as you're imputing all the ties around those sort of constant observed ties. Two, it's worth noting that you're able to impute a wider range of edges or missing edges than you did with simple imputation. So not only do you impute ties going from non-respondents to respondents who nominated them, like E to D, you can also extend that to any respondents, so any ties from non-respondents to respondents, as well as ties between non-respondents. And so a much more holistic, much more sort of general approach to imputation. All right, so what I want to do is just jump into what kind of the doing of it, because in some ways it's easier to see this in action. And so what I've done here is just present, as you can see, a brief example in R. I'm not going to go through the syntax, line by line, as I'm going to basically just going to give you the logic of it, or the form of how you go about implementing these imputation approaches, and then the actual code will be up online later. Okay, so first, yes, we're going to start by loading some packages, and we'll read in the data, and that will be with the R code as well. When you load in this r.r data object, there's this r data file, there's two objects there, mat and attribute underscore dat. So the mat is the input matrix showing a friendship, in this case, in our little example network. So there's 72 nodes in the network. In this case, we can assume the relationship of interest was friendship. So a 0 is an observed 0. That means, so for example, person 1 did not name person 2, 3, 4, or 5 in as a friend. A 1 means they did name them as a friend. So person 3 named person 1 as a friend. But then you also see, even amongst the first 5 rows and columns of this matrix, there's missing data, and those are the NAs. And those are cases where you do not have information if the person in the row nominated the person on the column. And the way this particular example is structured, there's NAs across the entire row. So person 2 just was absent, we'll assume, that day of the survey and didn't fill it out. And so we don't know if person 2 nominated person 1, 3, 4, 5, and so on. Okay, on the other hand, we do know who amongst the respondents would have named person 2. So we know that person 1 did not name person 2 as a friend. We don't know if person 2 would have named person 1 as a friend, for example. What else do we have? This is attribute data. So each row is an ID or an actor in the network. We have so 2 variables. That miss column is just an indicator if that person is missing or is a non-respondent. So person 2, you can see all the NAs across the row. So you get a 1 in the miss column there. And status is just kind of a attribute in this case. Are they high status in the network? Okay. And you can see here, I also did a little table to show you that in this case, we have 14 people who are missing and 58 people who were not missing in the network. Okay, so in this slide, I'm just kind of going through the data network construction, and I'm plotting it, coloring the nodes by whether or not they were missing or they were non-respondents. The important part of the picture is that, so in this case, I've colored the non-respondents with the missing folks brown. And so what's important is for those folks, there's only ties going to them. There's no ties going back. There's no outgoing ties. So we see you can nominate a brown node, those non-respondents, but the non-respondents have no ties, no outgoing ties. And so you're getting some information about them, but there's missing data. All right. So what to do? I'm going to basically show you how to implement those three different strategies that we talked about before on this little example network. And again, I'm not going to go through the kind of details of the syntax, but just give you a sense of how the logic of how you go about it, and then a little bit about what it might yield. So start with listwise deletion, in which case we're just, so I put the little toy example plot up top. And as a reminder, this is the case where you just delete those non-respondents. And so they're not included in the constructed network, and there's no ties going to them. And of course, no ties going from them as well. And so in terms of doing it in R, fairly straightforward. It's really just about identifying which nodes are missing, and that's kind of going on here, and deleting them from the network, and then taking that network where those folks are removed and using that as the sort of network of interest. And then I plotted it just to kind of give a sense. So first, yes, and I've also colored it. You can see there's no brown nodes, no non-respondents, because they've been removed. The network looks distorted, if nothing else. So if you can go kind of back to what that looked like, if you look at the network, once you take out those non-respondents, you get kind of longer chains. There's not as strong of a group structure, and just looks less interconnected. And so we clearly, there's a consequence to taking out these non-respondents. We're getting a distorted picture of the network. And in general, yes, the listwise deletion is probably the worst choice you could do in terms of dealing with missing data. Second one, a little better. Here we're moving to the case of simple imputation. So this is the case where we're going to keep those, for the most part, keep the non-respondents in the network as long as anyone nominated them, and then do kind of a light imputation back on, as he in quotes, the return ties. So a respondent nominated those non-respondents, then we're just going to impute whether or not they would have returned that tie had they filled out the survey. In this case, we're going to impute those missing edges going back to the respondents using a probabilistic option, basically flipping a coin based on the observed rate of reciprocity. And so I'm not gonna spend too much time on this. The example is sort of worked out in full detail in the R code, but I give you a flavor for it. So basically, first you need to calculate the observed reciprocity rate. Note this is on the observed network, so just on that network we just constructed using listwise deletion. So that is what you would use to sort of best guess as to the reciprocity rate. Then the rest of this slide is mostly just kind of getting the data into shape. And here, using this R binom command, once we get the data into shape, that's when we take draw. So flip a coin for every sort of case of interest where there could be a return tie from a non-respondent where there's no information to a respondent who nominated them. Kind of flip a coin using the observed rate of reciprocity we calculated in the previous slide. Flip a coin, take those flips of the coin, zeros and ones, and use that as to say if and not if to help impute those missing edges. And the rest of it is to kind of construct the network given those imputed ties. But I won't spend too much. I won't say anything more about that. Okay, so I want to spend a little bit more time on the model-based imputation. This is sort of the last approach. Okay, so a reminder, with model-based imputation, you start by estimating a model on the observed network or on the full network conditioned on the missing data. And the idea is to predict where ties exist based on underlying tendencies. So in this case, we're going to do a simple model. Edges, so we have a term for edges, we have a term for mutual reciprocity, and a term for, say, absdiff on status, basically a homophily term saying whether or not people who are more similar on status are more likely to have ties. Okay, so we use the ergem command in R. We estimate our model. We get our three coefficients. What's the intuition here? The intuition here is that, so we have a positive coefficient on mutual, and that tells us that ties are more likely to exist if they're reciprocated than if they are asymmetric, okay? Which sort of, as suggested before, suggests when we use this to simulate or impute ties, the E to D edge should be have higher weight or higher probability than the E to C edge, because the E to D edge would create a mutual tie, while the E to C edge, if you imputed that one, it would not. Similar ideas with the absdiff status term. Basically, this tells us that so a negative coefficient tells us that when people are really different in status, they are less likely to have ties, which means that when you're going to impute missing edges, if the two people involved, the non-respondent and then the respondent they might send an edge to are different, or really far apart on status, the tie is unlikely. Okay, so that's sort of intuitive. We're going to take these tendencies that so where we see an edge would become reciprocal and the status between them is pretty close, we should be more likely to impute that edge when we go to actually do the imputation, which is what we do right here. And we're going to use the simulate command. So we're going to take that mod, which we estimated, that object mod, that's the estimated model from the previous slide, and we're going to use a simulate command. We're going to basis equals net. That tells us that we're going to start with the network with the missing data as the kind of starting base. We're going to do one simulation. That's the end sim equals 1. And important, we're going to constrain that simulation when we predict where edges should exist. And we can constrain it on the observed edges. What does that mean? That means if we know, like in the original matrix, there's a 0 or a 1, so we know there's a friendship or not a friendship, we're going to hold those fixed. We're just going to assume that that is true data or observed data and not sort of allow it to change when we do a simulation. We're only in this case interested in imputing edges which we don't know about, those NAs in the matrix. Okay, so you simulate in this case just once. You get this net underscore sim1 as the network of interest, and then in this case we just plotted it. And in this case, what I've done here is plotted the original network by the imputed network, and I've plotted it so that the coordinates are the same. So the nodes are placed in the same place. So what's the story here, or what's the sort of payoff from the imputation? Well, you can see, what's different is that there are now edges going out from the non-respondents. So in the original network, there only ties 2 non-respondents, but with the imputed network, some of those missing edges are now at least our best guess as to what they might have looked like had they filled out the survey. And so, for example, we see a disconnected triad in the left-hand original network, while in the imputed network, those disconnected triad is in fact connected to the rest of the network. It's sort of a possible, and of course has implications for diffusion and connectivity and the like. So one more slide on the R side of things. I'll just note that because it's stochastic, same thing with the probabilistic option as well. You're gonna want to do this multiple times. Each time you did a simulation, it would look a little different. And in this case, we're going to do it 100 times. What would you do if your 100 networks at the end of it, or 1,000, whatever many times you want to do this? Well, you could basically use that 100 networks or what have you as inputs into your own analysis. And so each time, basically using the imputed network as the version of the network that you used to to calculate your statistic of interest, or to use as inputs in the simulation, or depending on what the analysis look like. In this case, I've just kind of done a simple summary on the density of the 100 networks, just to get a sense of the range of values. Last comment is that we use a really simple model in this case, but you could do much more complicated things, add more terms. You also put different constraints on the simulation. So for example, if you wanted to put a kind of a top end on how many edges are allowed to be added, so if you're worried about over imputing, you can put degree constraints on those non-respondents. And I'll just sort of end, or almost end, by showing up some past results on, okay, if you did these approaches, simple imputation and model-based approaches, and you compared it to sort of doing listwise deletion, just sort of took those the non-respondents out and sort of went with that. What are the returns to imputation in terms of reducing bias? And the answer is, this is really centrality measures, but very similar with everything with other types of measures, is that yes, listwise deletion is almost always the worst, and the returns to imputation can be quite large, especially if you use sort of the right approach for the right measure and the right scenario. But almost in every case, it's better to do something other than listwise deletion. And this is a little summary of, for centrality, what is the best imputation approach. And it varies scenario to scenario, but it's very rarely listwise deletion. Okay, so let me wrap up and say that network data are often incomplete. This is a very common problem. It can create biases when constructing your network, which has implications for using network properties as predictors or as outcomes. It also has implications for identifying proper targets for an intervention, so figuring out who is the most central actor, as well as using it as inputs to network-based simulation. But I think I hope I've convinced you that with reasonable imputation choices, and they're not that hard to implement, I think, you can greatly reduce the problems of missing network data. So it's worth doing even simple imputation in most cases. And so I'll end by saying that you should feel free to contact me if you have any questions about the R code or about the slides, and I'm happy to chat about missing data in general. All right, thank you.